Welcome to Study Loop.
Hi everyone, thanks for joining me today. We're going to be looking at principles involving work and kinetic energy. What we have is an asteroid shown here, starting a very large distance away from the Earth, that is shown here. And what's happening is the only force that's acting on this mass is the gravitational attraction from Earth. And what we're asked to find is the velocity at heights above the surface of the Earth at 8,000 kilometers, 50 kilometers, and then when the asteroid hits the surface of the Earth. So, we're given the radius of the Earth of 6,370 kilometers, and what we know is that the kinetic energy at the beginning is equal to 0 because the asteroid is starting from rest. We know that kinetic energy at the points that we're interested in is simply 1/2 mv squared. And we know that the work done by the forces at play here is simply going to be given by F times dr. So we know that the only force at play here is the force of attraction, and for planetary bodies, that is simply going to be, so we have F dr, which is the work, and we're going to plug in for F, and we know that is going to be minus mg r squared over r squared dr. So we are going to be evaluating this integral from r equals negative infinity to our radius of Earth plus h. Now h is going to be those different heights that we're looking at. We have negative mg r squared over r squared dr. So, because the kinetic energy in the beginning is equal to 0, we know that the work is going to be equal to the final kinetic energy. And this can be written out as saying that 1/2 mv squared is equal to the integral of negative infinity from re plus h of negative mg radius of Earth squared over r squared dr. As you can see, our masses cancel out, which simplifies this expression, this equation. What we're left with is v squared over 2 is equal to negative g r squared, radius of Earth squared, of the integral from negative infinity to re plus h of 1 over r squared dr. Now when we evaluate this integral, what we get is v squared over 2 is equal to gr squared 1 over r evaluated from negative infinity to re plus h. Now this is a pretty simple equation to solve. We know the value of this r is just re, and this radius of the Earth that's given to us. We know the value of g, that's just gravitational acceleration of the Earth. These h's you can plug in for. Those h's that we're interested in are h equal to 1,000 kilometers, 50 kilometers, and 0 kilometers. So as you can see, we actually have all the information that we need to actually go ahead and solve this equation for v. And once you plug in for h and re, you get that the velocity at 1,000 kilometers is equal to 10.39 kilometers a second. The velocity at 50 kilometers is equal to 11.135 kilometers per second. 1.135 kilometers a second. And the velocity when the asteroid hits the surface of the Earth, so that's going to be velocity at h equals 0 kilometers, is equal to 11.18 kilometers per second.